Welcome to part 17, analysis design of a flyback. And the topic that I'm going to cover is the leakage inductance. I know that I've went through very briefly the leakage inductance, how it affected, but I want to go in more detail. And the reason that I want to go into detail is that in my designs, since I design power supplies for space application, the voltage that I use is typically from 24 volts to 34 volts. So basically it's low voltage. However, I have received feedback from many of the students that are designing power supplies or universal power supplies where the RMS current is anywhere from 85 to 265 RMS. So with those type of voltages, you end up with a huge voltage spike. And if you don't design your transformer properly, where you minimize your leakage inductance, you end up with a very large voltage spike. As a matter of fact, the voltage spike at the drain of your MOSFET can exceed 1,000 volts very easily. Okay, so I'm gonna try and explain in detail. Hopefully I'll make sense of the analysis. Okay, so I'm gonna go through a quick review. Basically, what is the leakage inductance, how to model the leakage inductance. It's basically a little bit of a review, and then how it affects the circuit, and then I'm going to try and do a mathematical equation and do a SPI simulation to verify my equation. Okay, so that's the topic and what I'll be discussing today. Okay, quick review. What I'm going to be using, I'll be using the ideal model, transformer model, instead of the coupled inductor model. And I'm going to assume that this transformer is ideal. Okay, this is an ideal transformer, and it has a 1 to NR ratio. This would actually be N, P, and S. Turns in the primary, turns in the secondary. And this will be my R primary. Okay, so this is your magnetization inductance. Okay, and the leakage comes about because there is no such thing as an ideal transformer. Okay, there's always imperfections, and in a perfect world, whatever flux is developed in the primary, if you have 100%, then all the flux would be linked to your secondary. Okay, but because the windings may be uneven and there's spacing in between, and sometimes we don't have same turns ratio, they don't all get coupled, so you end up with what is called a coupling coefficient. Okay, and that coupling coefficient is basically a percentage of leakage inductance. In other words, certain windings are not coupled to the primary, and the way they act, since they're not really coupled, any energy that is in the primary doesn't get coupled to the secondary, so it's uncoupled. So basically it's like adding a parasitic inductance. So that's what really the leakage inductance is really a parasitic. It's something that you really don't want. Okay, so in an ideal, you don't want no leakage. Okay, but of course can't have that. You'll always have a little bit of leakage. Okay, so this is a model that we have. You have your MOSFET here, And the way I'm modeling the MOSFET is just a switch, and I went ahead and added the capacitance from the drain to the source, which would be this C MOSFET. Okay. So again, leakage inductance is due to the uncoupled windings between the primary to the secondary. Okay. Then, short review. How do you measure the inductance? Well, if you have a primary or a transformer, all you have to do is you get your secondary windings and you short them out. Let's say if you have a transformer with multiple windings. Okay, so what do? You short all of them. You short all secondaries, and with all the secondaries shorted, what it does, it basically looks like your primary inductance is shorted. So when you connect a LCR meter across the primary, you're actually measuring the leakage inductance. Okay, so that's how you measure, and it's very important that when you wind your transformers, that you measure first your primary, and your primary, let me go ahead and write this. Your primary, you measure with the secondaries open, and your leakage with the secondaries shorted. So it's very straightforward. I believe if you go to video number 6, I actually wind the little transformer and I measure it. So some of you may have already seen that. Okay, so let's see the analysis. Let's see what's happening. Okay, again, ideal transformer, and this is the time. This is the T on schematic. Okay, and for this, I'm going to go ahead and use 82 volts as my V input. Okay, and during this time, your MOSFET is shorted. Okay, so during this time, you're going to have current. Let me use a different. You're going to have current flowing in this direction. Okay, so from this, you can see, hopefully, that the current going through this primary, and I can call it I primary, okay, is written here, but that I primary is actually also flowing through the leakage inductor. So if these are the same, you can make a statement that the I primary is equal to the leakage inductance. So that's one assertion or statement that you can say. Okay, but the same token, you can say that it's also the same as the I MOSFET. Okay, and during that time, the sign on the primary is positive on the dotted. So if you have a positive on the dotted, that means that you're going to have a positive on this dotted, and therefore you have a negative on the non-dotted, a negative. And if you have a negative, remember there's a diode here, and since you have a negative going to the anode, the diode is off. So if it's off, that means no current. No current through secondary. Okay. So basically, what you're doing here during T on, you're storing energy. And typically it's in the gap. There's a little gap that you grind, and that's where the energy. Okay. So this is the storage phase. Okay. So now you stored energy into your primary, but you also stored energy in this leakage inductor. Remember, the leakage inductor it's one of the windings that is not coupled. Okay, so now it brings us to T off. And T off is the time when the MOSFET is open. So here I have the switch, the MOSFET is open. Okay. Now keep in mind that prior, during T on, you had current going through the primary, and because of Faraday's law and Lenz's law, that current wants to keep flowing in the same direction. Okay, but this current that is flowing through the primary, because this is coupled to the secondary, okay, this current, or the energy that is through the primary, or rather the gap, then is allowed to transfer to the secondary. Okay, and during that time, the signs on the primary change. This was positive, now they flip because of Lenz's law. Now you have negative and you have positive. So you have a negative on the dotted, that means you're going to have a negative right there as well, and a positive. And if you have a positive, this turns on, so basically you have a short. Okay, and if you have that, then you can make a statement. We'll say that this is, we can say that this is V secondary. So we can make a statement that V secondary is equal to V out. Why? Because the diode is turned on. Okay, so basically that current that was flowing through here is transferred, and now you have I secondary. Okay, well, is the current I secondary the same as I primary? Well, no, it's not. It's proportional to it, and it's proportional to the turns ratio. Okay, how is it proportional? Well, here's the equation. I secondary is going to be I primary times N primary divided by this N secondary. Let me go ahead and make sure that this is clear. This is N primary and secondary. Okay, so that current flows in this direction. Okay, so we've taken care of this, but you have to keep in mind that the current or energy was also stored in the leakage inductor. Okay, and this leakage inductor can't flow in this direction because it's not coupled. Okay. So what it does, some of the current actually goes and flows through the capacitor, and you can call it a displacement current. Okay. And this current actually charges the capacitor up, and the flux in the inductor goes to 0, but then this is charged, so then it recreates the flux back on the leakage inductor, and it goes back and forth, and what you get is you get ringing. Okay, you'll get a decaying ring. So that's where this leakage current is going through. Okay, so now that you have that, or at least that understanding what happens, that this primary current, because it's coupled, is directed to the secondary, but this leakage inductance does not get coupled to the secondary, but rather stays on the primary side. Okay, so next question would be, then what is the voltage across the drain? Okay, so here we have this schematic. Okay, and what I did is I went ahead and brought this the source, I brought it out here, so you can do a Kirchhoff voltage loop. Okay, and if you go in this direction, okay, you can see that you exit the positive, and we can call these V input. So this is a positive. Okay, and then during that time, remember, this is negative and positive. We're going in this direction, we're exiting a positive, so we have positive VL primary. And again, this is negative and this is positive because the current was going in the same direction. So then you have a positive leakage, basically the voltage across the leakage inductor. So then you end up with V MOSFET. Okay, and since we're going in this direction, it's leaving the negative side, so that becomes negative V MOSFET, and that means that it's KVL means you sum it to 0. Okay, so then we solve for V MOSFET. Basically it's the drain. So now you get this equation, Vn plus VL primary plus leakage. Okay, but let me define this a little bit more. V primary. Okay, in other words, it's the voltage across this voltage right here. Let me define that a little bit more. Okay, you can write this equation. This equation is your general transformer equation. Okay, and if you solve for V primary, you end up with V L pri is equal to V out times secondary turns divided by the secondary turns. Okay, now if you notice here, there's another statement that you can say, since V sec and the diode is turned on, these are equal. So then I can substitute that into there, so I end up with this equation. Okay, so that equation then is inserted into VL pi. Okay, so we're down to here. Let's see. Okay, and let's say this is MOSFET drain. Excuse me. Okay, so now we have this equation, Vn plus, and this VL pi is actually V out times NP, secondary, primary turns divided by the secondary turns, plus V leakage. So what is this V leakage? How can we express it? Okay. Okay. Basically, that's the voltage across the leakage inductor. Okay. And you could use this equation if you know what your delta current is. In this case, we do know what the delta is. It's I pi, but we don't know what dt is. It would be something that you would have to measure. Okay, so that's a little harder to do. So, but if you did know it, then you could easily find out what the leakage inductance would be. So we're going to use a different method, and perhaps it may be a little bit more intuitive. Okay. So number 5, we're going to treat the leakage inductor as a current source. It's a very important concept. Okay. Why am I going to treat it as a current source? Well, remember that the inductor has stored energy, and prior, when it was storing the energy, it had a current of IP, or primary, going through it. Okay, so when it's released, that current keeps trying to flow. Okay, and it does flow, and I said that it flows through the capacitor. In this case, it's a CMOSFET. Okay, but in addition, some of it does flow through the L primary, or actually not the L primary. Okay, this is L leakage. Okay, so you can model this as the leakage inductor. Okay, so basically this is a little tank circuit. It's a tank. Okay, and because it's a tank, there's a formula that you can use to simplify this. Okay, since it's a tank, remember a tank oscillates, and remember when the leakage, you have the leakage inductance, it's oscillating, you have this little ringing that you get. So you can use this concept. Okay, and by using this concept, what you can do, you can simplify and say that this current is going to flow in this direction into the tank. Okay. So then you can modify this circuit, and you can say that the impedance, the characteristic impedance of the tank is defined by the square root of the leakage divided by C MOSFET. Okay, so basically this current, remember it's I pi, is going to flow in this direction, and if it flows in that direction, then you end up with a negative and a positive in that direction. Okay, so now you can make a little further simplification. Since you have current here, and that current is flowing through an impedance, then this becomes a voltage spike or a voltage source. So then this becomes a little voltage source. Okay, so now you can come up with an equation using that model. So you can say that the voltage leakage is actually I leakage, in other words the current going through the leakage inductor, times the impedance. Okay, and we already said that that equation, you can substitute it in here, and you can also make this substitution, because we know that the leakage inductance is equal to the I pi inductance or current. So then you come up with this equation, very important equation. This describes your leakage spike. So basically, this is your spike due to the leakage. Which is I primary times the square root of your leakage inductance divided by the CMOS. Okay, so now we're going to try and put everything together. Okay, so the voltage across the MOSFET at the drain is equal to V input plus V out divided by the turns of the primary divided by turns of the secondary, and then this is where that goes in here. So again, mind you, this equation is the voltage spike. Okay, this is not wanted, basically. Not wanted. Or undesirable. Okay. So, and why? Well, let's say you have a MOSFET that is rated for 500 volts, and let's say this, let's say the leakage spike adds 200 on top of 500. You will certainly exceed the voltage rating of your MOSFET. So what you want to do is you want to reduce or you want to minimize the voltage spike. So what can we do? Well, we can take a look at the equation that defines the leakage. Okay, we can reduce your primary current, but that is set by your design. So typically you can't change your current going through the primary. Okay, but these, you have a little bit of control over these. Okay, the one that you have control is the leakage inductance, and that is determined by how well you built your transformer. Okay, and there's some techniques. Hopefully they'll show in the next video. We'll try some of the techniques and see if they help or not. But from this equation you can see that if you minimize your leakage, that minimizes your voltage leakage. And if your CMOS goes up or increases, then that also minimizes your voltage. So in a way, let's say your capacitor MOSFET is 100 picofarads. Well, you may be able to add a external capacitor, and since there's the capacitance between the drain and the source, if you add an external, they add up. So there's a way of manipulating that term and reducing it. Okay, so now here's the equation. Okay, and I went ahead and did this mathematical or script. Okay. By the way, if you would like a copy of this Mathcad script, email me and I will send you this along with the spice. And let me go ahead and open this up so you can see what I did. And it's actually a design tool. Let me go ahead and just show a little bit. Okay. And basically, these in green are my specifications. So in this case, I have a V input minimum of 82 volts, and I'm going to assume an efficiency of 80%, duty cycle 42, frequency of 100 kilohertz. And for right now, for this analysis, I'm going to go ahead and use a CMOS FET of 10 picofarads. That's very, very low, but I just wanted to make a noticeable voltage spike. Okay, remember, if you make this CMOS bigger, it reduces the voltage spike. In this case, I left it small, that way the voltage spike would be higher. And I'll be using a leakage inductance of 18 microhenries. Okay, and on this one, I'm going to go ahead and assume that my voltage is 5 volts, 2 amps. And if I wanted a second, third, and fourth, I could type in my any voltage that I want, any current, and what it does, it totals my current, totals my output power. In this case, I'm 10 watts. Okay, and I gather my total power here, divided by the efficiency, so I get my input power. Okay, basically this is all the equations that I have covered throughout the video series. So V input divided by the minimum voltage gives me my average current at the primary. Then if you divide that by your duty cycle and this constant, you get the peak. So I got that peak. And then for my simulation purposes, since I'm using a PWM, the way the PWM works, it has to have an I sense of 1 volt to reset the MOSFET. So I set my ILEM to 0.9, so I get 10% margin. So my resistor to sense my current through the primary will be 1.24. Okay, and then this is the same equation that I've been using throughout. Yeah. Okay, and of course here's the turns ratio and so forth. And in this case, with the primary inductance of 477 microhenry and a leakage of 18, I believe, the coupling coefficient is 98%. Okay, typically that would be good, but however, even though it's 98%, you still end up with quite a bit of current. Okay, so this is where let me go ahead and close that. Okay, so here I find out what the resonant frequency, since it's going to be ringing, I know that it's going to be ringing at 11.8 megahertz. And here is where I calculate the characteristic impedance of the tank circuit, basically between the leakage inductance and the MOSFET. So in this case, I have an impedance of 1.3K, which is rather high. Okay. Now the voltage before you add the voltage spike should be 164 volts. Okay, that's the voltage without the voltage spike. But if you add the voltage spike due to the leakage, here you have I peak times the characteristic impedance. If you notice, it's 970 volts. That's a huge voltage spike. Okay, so here I have the final equation, Vn divided by V out divided by NR1, which is really, NR1 is the turns ratio of the primary divided by the turns ratio of the secondary. That's what NR1 is. So I will get 1,135 volts on the drain, basically. Okay, so now my inductance 477, leakage 18U. Okay, I already done the simulation, and here it's regulating at approximately 5 volts. Okay, oh, let me go ahead and re-simulate it because I actually added a snubber. So I'm gonna put a T here, which removes the snubber, and I'll re-simulate it. It'll take a little bit of time. So the Mathcad script shows that I should have close to 1,100. And let's see how accurate or how close we get to that. almost halfway done. Almost there. Okay, it's regulating. Okay, and if you notice, okay, let's see what we got. So this is the drain voltage. Okay, and let me, before I measure the voltage, okay, calculate it. This is 717 milliamps going through the primary. I believe I have that here. Let's see. Yeah, calculated 723 milliamps. So that's pretty close. 717 milliamps. Then I put the cursor here. Let me go ahead and delete these. Clear, clear, clear. Okay. There we go. So we have a little bit over 1,000 volts. So we have 1063 volts. Okay, and the script 1135 volts. That's pretty good. Okay, so how can we reduce it? Okay, well, what we can do, one of the things that we can do, we can put a little snubber. Okay, and I'll go ahead and show the math regarding that. The snubber has to be the same impedance as your tank circuit. So I'm going to use a 1342, or actually 1342 ohm. Okay, and it's going to be in parallel. That resistor is going to be in parallel with the impedance of the snubber. So basically, it's going to be, this will be the snubber. Oh, I'm sorry, and your snubbing capacitor. Basically, it's going to be a resistor and a capacitor. So here's a resistor and here's a capacitor, and all of this basically. Let me go to the schematic. So it's basically this is in parallel with this, and remember this is Z out. So basically here's Z out times the impedance of this. And if you recognize this, this is the R1 times R2 divided by R1 plus R2 is the resistor. So it's the parallel resistor impedance. So basically I have impedance of 672 together combined. So basically I've lowered it from 1342, which is the characteristic impedance. I halved it. So basically I'm reducing it by half. approximately. So according to this, with this number, it should come down to 651. It's an approximation. Okay. So in this case, I'm going to use C's number as 1,000. No, I'm sorry, 100 picofarad. And my resistor is going to be 1342. 1342. That's 10. And let's run it again. You can fast forward if you like to get to the simulation results. Now keep in mind these are not going to be exact, they're approximation, or at least it gives you an idea of what you can do, or at least what is possible or feasible. And like I said before, if you're interested in the Mathcad, drop me an email and we'll send you the Mathcad along. Keep in mind it's version 14. If you don't have Mathcad, I'm pretty sure that you can put the equations in Excel. Should be able to do that as well. Okay. Okay. So now let's go ahead and again, let's delete the first, third. Okay. And let's zoom in here. And if you notice, you don't have that ringing anymore. Okay. So now you have approximately 605 volts. Okay. And this predicted 651 volts. Okay. Now let's backtrack a little bit. Okay. Basically, the leakage inductance is adding 486 volts to the drain. So if we didn't have the spike, the drain would have 164 volts. Okay. So let's see if that's true. Well, this is the leakage spike. The actual voltage or steady state should be this part. And if you move this here, notice it's 165, 173. So basically this is the actual voltage. So this entire spike from here on up, that's an additional spike. That's an additional voltage that the leakage inductor is adding. Okay. So in the next video, I'll see if we can design a clamp circuit that will minimize that. Okay. If you have any questions, please feel free to email me. I know it was quite a bit of material. Also, if you would like some of my notes, those are available as well. Thank you for watching. Thank you.